What I want to talk about next is ember pyrometry. And as far as the big picture, people are really concerned about firebrands and wildland fires because they seem to be responsible for about half of the homes that are destroyed in wildland fires. And they really accelerate the spread rates of these wildland fires. But not much is known about them. And of course, anytime you're burning wood, it's going to be very difficult to do the measurements. But one thing that you can measure pretty well with wood burning is the temperature. Now, if this is an ember that is 6 millimeters in diameter and 20 millimeters long that's burning. It's a piece of maple with a small fan blowing on it. And you wouldn't want to try to measure the temperature with the thermocouple because the thermocouple makes poor contact and it quenches the reaction. But you can measure it just with the camera by doing pyrometry. And so that's what I'll show in today's installment, the next lecture. And I should acknowledge the sponsorship here from NIST. NIST sponsored this work, and also UL, formerly called Underwriters Laboratory. And the student authors are shown here, James Baldwin, Nicholas Bouvet, Kyle Decker, and Dennis Kim. These are some pretty dramatic pictures of firebrand showers. And it looks kind of like snow. It looks like a snow blizzard. These burning embers swirling around. In both cases, these are firefighters that are pretty well protected against it, but you can tell they're not too comfortable, even with their good turnout gear, to be showered by burning particles. And it's really dramatic what these can do. It's such an onslaught into your house or into your unburned fuel that can start new fires. The way these usually ignite fires is that it's not usually one firebrand that lands and starts a spot fire, but usually they accumulate from turbulence and vortices, kind of like the leaves that you may find in your driveway after a windy storm. They tend to accumulate in piles. Once you get a pile, it gets to a critical mass, has enough heat flux that it can heat up the wood underneath and get that burning, especially on your roof or on your deck. So it's only been in the last few years that there's been a real emphasis on research on firebrands and understanding how these things can propagate fires so efficiently. So this is the motivation. Firebrands have been observed to travel up to 9 kilometers. That's kilometers. If you imagine you're a firefighter and you have a river or an interstate highway and you think you have a good fire break, not necessarily. There's no river, there's no interstate highway that's 9 kilometers wide. And also firebrands are responsible. It's a little hard to estimate, but it's estimated about 50% of the structures that are burned, the houses and the other structures. Now, the firebrand temperature is an important aspect of these firebrands, and it's something that can be measured, but until now hasn't been measured, at least not very accurately. And it's important for looking at the burn time and the propensity for secondary ignition. If a firebrand is super hot, it's a good ignition source, but it may burn out before it lands. If a firebrand's very cool, it may extinguish, or when it lands, it may not be hot enough to start a fire. So understanding the temperature will be very important. And hopefully then, the temperatures that we're measuring for these can be used in CFD models to predict fire spread. So lots of people have done pyrometry on embers in the past. And most of this work is summarized here, but most of it, they use infrared imagers. Anybody who's seen a firefighter, often they have on their hip an IR imager. They hold it up, and it's actually a low-resolution device that has basically a bunch of heat flux sensors. And then you view the heat flux in the screen with these IR imagers. Unfortunately, for embers, they usually have been validated with thermocouples. And as I mentioned, thermocouples aren't a valid way of measuring smoldering temperatures. And so they try to accommodate for this and get reasonable temperatures in the end. But often that is a limitation. The people have reported temperatures in the 800, 900 degrees C range. That's kind of what we're seeing as our mean temperatures, but also at much lower temperatures, 500 to 600 degrees C. So it's always hard to compare because with wood burning, you have to have a lot of wood burning, a lot of data to get a good statistical sample. Some people have found that wood ignites at about 190 degrees C, and sometimes people have used infrared imagers to estimate the temperatures. Luckily, camera technology has come a long way in the last 20 or 30 years, and that's why you can see most of these are more recent studies. But we have this situation now for $1,000 or $2,000. You can buy a state-of-the-art SLR camera that can do the most amazing pyrometry. When I was a PhD student, we did pyrometry of soot. And soot's a great place to do pyrometry because you can put a filter on your camera, take a picture, put a different filter on your camera, take a second picture, and from the ratios of these, then determine the soot temperature. Not only that, you can also measure the soot volume fraction with this. And what we're doing here is something a little different because instead of looking at soot, which is a little tricky because you have then a line of sight that has to be accounted for with maybe onion peeling or Abel transforms, we're looking at a solid burning. And the other thing that we're doing that's different is instead of using filters, actually accepting the filtering that happens in every camera. Every camera from your cell phone to your SLR actually filters red, green, and blue on the different pixels. So we're taking advantage of that native filtering. This is a study out of Berkeley, Carlos Fernandez-Peyo and James Urban at Worcester, where they did ember pyrometry on wood embers in a wind tunnel. And here they compared actually an infrared camera, a FLIR camera, with a Nikon camera and got temperature distributions that are shown here, and were able to compare the two. The thing that I want to draw your attention to is that infrared camera has relatively low resolution. Those are kind of fuzzy images. And by the way, the camera that they use here is a $100,000 infrared camera, if I'm not mistaken. And then the color pyrometry has much better resolution, but does require some more careful calibrations. So that's what we're going to do in this work, is talk about measuring temperatures of glowing surfaces with using just a SLR color camera. So I mentioned a couple times already, you can get the smallest thermocouple you can find, 25 microns, 50 microns, but as soon as it touches a glowing surface, it's likely to quench the reaction and have imperfect thermal contact. So for two reasons, you're going to measure temperatures lower than the true temperature near that region. Another way that you could consider measuring these ember temperatures is with infrared imagers, but these are very expensive, some of them up to $100,000. You get low pixel counts, they're low response times, and at some point you have to specify the ember emissivity and the transmittance. In fact, you multiply those two together, but if you have ash or smoke, it extinguishes, it absorbs some of the photons and needs to be accounted for. And if the surface of the ember isn't at an emissivity of unity, usually it seems to be around 0.8, that needs to be input into your images. Certainly, we're interested in doing the pyrometry of these flying embers, and there's some uncertainty about what the wind speed is for a flying ember. It's expected that they travel at their terminal falling velocity. They basically follow the wind currents, except they fall at their terminal velocity, but it's still not known what their temperatures are. So with that background, these are our objectives. So we want to measure images with imaging pyrometry, the temperatures of smoldering embers. And as a second step, what we want to do, and what I'll show, is that we spin the camera. So really, ideally what you want to do is have your camera fixed, have a bunch of firebrands flying by, you take images, and from the streaks, you back out the temperatures. But that's a hard measurement, and once you do it, it's hard to be sure that you got the right temperature, because there's no ground truth. There's no way to be sure of that temperature. And so what we've done instead is actually to spin the camera. We keep the ember fixed and spin the camera. It's exactly the same image as you get, and you can analyze it. And what we found is that it does give you the correct temperatures. And in the third objective, what we're finding is that with this pyrometry, we can measure not only the temperature, but we can also measure the emissivity times the transmittance. So how much ash and smoke may be absorbing the light, and what's the emissivity. And finally, if you know the temperature and the emissivity on a pile of embers, then you can use shape factors and predict the radiation at any point. And I think this could be a useful method if someone wants to burn a Christmas tree, for example. We do lots of measurements where you take a heat flux gauge and you get the total heat flux from the Christmas tree. But with this method, it should be possible to take images with this camera and know how that heat flux is distributed and map it to any position in the room and estimate what heat flux would occur there. So those are kind of sort of 3 journal papers that are presented in these 3 sections. I mentioned that these infrared imagers are expensive. They're great. I would love to have one. I'd just love to have it for research, but I just don't have $100,000 to spend on them. Not only the camera's expensive, but the lens also has to be transparent in the infrared, so the lens is expensive. And then once you drop this $100,000, you look at the pixel resolution. So for both the FLIR cameras, these are in the range of, a half megapixel or a quarter megapixel. It's nothing compared to your cell phone. So for $100,000, it's nice because it's really measuring the infrared intensity. Every pixel in this thing is actually measuring heat flux. It's basically 500,000 heat flux sensors. It seems like a very inefficient way to measure light. If you want to measure light, why would you measure the temperature of a heat flux gauge? And the answer is that's the best way to measure infrared light. Astronomers use this. If you want to measure infrared light, the silicon doesn't respond. But in the first row of this, I show our camera, the camera that we use for this measurement. And it's a color camera. It's a nice camera that you might use if you want to take wedding pictures or pictures of your vacation. It's 1,300, and it has, I guess, about 18 megapixels. So many more pixels to work with, and 14-bit depth at every pixel. The infrared images usually are 8 bits. So that means 2 raised to the 8th power at each pixel. You can get 2 raised to the 8th power intensity levels. But for a 14-bit camera like this, it's 2 raised to the 14th. So you get really tremendous signal to noise. The count values go from 0 up to 65,000. Okay, so if the bullet at the bottom, if you want to do embryopyrometry with infrared imagers, you're going to have to pay a lot. You're going to have low resolution and slow response time. And you still have to, in the end, estimate what is your emissivity, epsilon, and your transmittance, tau. And that can be important. The ash can absorb a lot of the light. Smoke can as well. Here's the camera. Here's a big picture of this Sony camera. It's RX10. We picked this because this is the same one that NIST has been using for their embryrometer. So I guess it's 20 megapixels, 14 bits at each pixel, gives you at each location, all 14 megapixels gives you a red, green, and a blue value. If you take a picture for 10 seconds with the lens covered, you get no dark current. It's basically 0, which is really nice. It's not noisy on its own. And it doesn't have we didn't use any shot or interference filters. Another way you could use this camera, as I mentioned, if you had a nice steady laminar flame, is to put a line filter in front of this, say at, 450 nanometers. And so then you take a picture of the flame at exactly 450 nanometers, pull that off, put on another line filter, maybe at 650, take another picture. It's really an excellent way to measure soot temperatures or smoldering temperatures. But this type of thing usually is slow and won't work well for fires. It takes you a second or two to switch the filters, and in that time, your fire can change. And so we decided not to use any external filters. You could be smart and use 2 cameras, both with filters on them, and trigger them at the same time, but they'll always be looking at slightly different things, and then merging these images together to do ratio pyrometry gets very difficult. And this image on the lower left here is called a Bayer filter mask. So what happens in whether it's a CMOS or a CCD camera, and all the cameras you have in your pockets on your cell phone, you may have 20 megapixels, and every pixel is going to have a little dot of paint on it, whether it's red, green, or blue. About half of the pixels are green, because our eyes are most responsive to the green of the sunlight. So about half the pixels are green, and then you have some red and blue pixels. And there's a lot of proprietary software in here. People have tried to back out and to understand for each camera, like the Sony camera, which pixel's green, which is red, and which is blue. And we haven't really worried about that because what Sony does is that at every location, whether it's a green or red or blue pixel, they'll give you the pixel value for all three. And it does some fancy interpolation. It says, okay, if I've got a red cell here and here and here, it interpolates to estimate the red pixel value in the center. You have to be careful how you open the images when you do the calibration. If you change anything, you just don't want to open this up in some kind of default application, because the default on computers is, of course, to adjust make the dark things black and the white things white and adjust all the colors in between. And really with these kind of pyrometry measurements, any quantitative measurements with the digital camera, you want to turn off all the automatic features. Automatic gain, automatic focus, automatic shutter time, automatic ISO. They're made for automatic so that anybody can just pick it up and take a great picture, but you don't want that in the laboratory. And on the software side, the analysis side, and the down end, you don't want anything automatic either. And so what we found is the best way is to save the images as the largest formats, RAW, and to open them using this open source software called DC RAW. And then what we do is we can open the images either in Python or MATLAB. Both are useful in different ways to obtain the R, G, and B values at all the X and Y pixels. And then from ratios, we're able to get the temperatures. And the way we calibrate the camera is with what's called a black body. So this is a black body furnace shown on the left here, where you can dial in any temperature from 600 to 1200 degrees C. Now, lucky for us, we find that the ember temperatures also, when they're glowing, are in that range, 600 to 1200 degrees C. Now, I believe if we had an ember that's maybe at 1250 or 1300 degrees C, we would be able to extrapolate a little bit and be able to get the temperature. But so far, we haven't had to do that. All our embers, lucky for us, are in the temperature range of our black body. So what we do is we turn on the black body. It takes about half an hour for it to come to steady state. You dial in the temperature you want, and it glows red, like this image here at 1000 degrees C. Then clamp the camera down, take a picture of it, and hover the mouse or hover basically MATLAB and Python for a square area in the center of this black body, and then do the calibration plots. And what we then do is calibrate the red and the green and the blue intensities with the temperature of the black body. So this is an image recorded at 2 milliseconds at 1000 degrees C, and that's how the black body works. It looks like a nice, inexpensive thing that anybody can buy in your lab for a few $100s, but I think the going price on this now is about $25,000. They're expensive because they're heavy. There's a lot of, a lot of metals will melt at 1200 degrees C, and it needs to be isothermal and black on the inside and calibrated and with a nice temperature controller. So it's a very useful device if you're going to do pyrometry, but also an expensive device. So the first thing we did is we said, let's make sure that the camera responds in a linear fashion. And so what we did here is on the y-axis, this is the intensity given by the camera as a function of the shutter time. And you can see you get a nice straight line behavior. Now, this wasn't a foregone conclusion. There's no real advantage to Sony or Nikon to make their camera linear. They're not expecting many scientists to use this and try to use it in a linear way, but we found that across very broad conditions, it does have a linear response. And that makes things easier. Now, if it weren't linear, you just program that into MATLAB and Python, as long as it's repeatable. So really, the most important thing for a camera, it's got to be repeatable. It's got to give you the same response every time you take a picture of the same illumination. And ideally, if it's linear, then it makes your calibrations easier. We did find that it responds, as shown here. This is normalized intensity, that last equation there, responds to the F number of the camera. Basically, that's how large your lens is open, the aperture on your lens. It responds to the time, inverse time, and the ISO setting. ISO is a tricky thing because when you increase the ISO, it increases the intensities that come out of the image. But there are two ways the manufacturers do that. One is just a math trick, and we don't want to have them doing math on the camera. So the other way is actually to increase the amplifier, the voltage on the amplifier. And with this Sony camera, we do believe that it's actually increasing the gain on the chip. And so the ISO is a true gain, an amplifier gain, not some kind of math. Any kind of math, I don't want the camera doing it. I want to do that in Python or in MATLAB. So this is a big, busy plot of all our calibration data. And gathering all this data takes weeks or months to do it carefully and to have a good calibration. And it's essential if you're going to use your camera for quantitative measurements of temperatures or soot volume fractions that you have a good calibration. What's shown here on the x-axis is the temperature of our black body, again going from 600 to 1200 degrees C. And as I mentioned, luckily that overlaps exactly with the temperatures of the embers we're measuring. And on the y-axis is the intensity of the red, green, and the blue pixels. And what I want to get across to you here is that the data is very well collapsed. When we change the ISO and plot it in terms of a normalized intensity, it collapses the data. If we change the shutter time or the F number, all these are accounted for nicely. What that means is when you calibrate it, then you can use it for different camera settings. If you need more gain, you can turn up your ISO. If you want to have a greater depth of field, you could change your F number, and that you can be confident that the math works and the normalized intensity scales with the black body temperature as shown here. So I also want to get across to you, look how many, this is a log scale on the y-axis. Look how many orders of magnitude you get in variation. From 600, the red scale, red is the most important one. You know, those pixels, when they're glowing, they look red. And you get about 4 orders of magnitude. So anytime you're doing combustion and you have a signal that varies by 4 orders of magnitude, you ought to feel very lucky. A lot of times you measure something and it only varies by a factor of 2. Even a thermocouple measurement, the thermocouple voltage output between a cold thermocouple and a hot thermocouple is probably a factor of 2. But here we get 4 orders of magnitude. So what this means is that if we use the camera and look directly just at the red or the green or the blue, we have excellent precision, excellent variation with these 2 to the 14th grayscale levels at each pixel. Okay, now, unfortunately, we can't just take a picture of an ember, hover over that pixel, find the normalized intensity by accounting for the F number and ISO and so forth, and then reading across this curve and finding the temperature. And why not? Because we don't know the emissivity times the transmittance. And that's given in that equation where it says, however, the ember energy is equal to the emissivity of the ember times the transmittance, usually by the ash absorbing about 5 or 10% of the photons, times the black body. So if you knew your emissivity times the transmittance, then you could back this out and use the calibration directly, what we would call grayscale pyrometry, going directly from one color, usually the red, to the temperature. So grayscale pyrometry, it's very precise. You get a variation of 4 orders of magnitude, but it's inaccurate. There's a bias. It's always going to give you temperatures that are too low, because if you're assuming emissivity times transmittance of unity, all the photons, the thermal photons, get to your camera. In reality, that value is closer to 0.8, and it varies with pixel. So in order to correct for that, in order to correct for emissivity times transmittance, which is generally unknown, you may have an ash pile on one part of the ember and ash that had just blown off on another part, what we're going to do is ratio pyrometry. So what I'll show on the next slide is it's the same x-axis, but now I'm going to take the red curve and divide it by the green curve, the blue curve and divide it by the green curve, and show how ratio pyrometry will work. And ratio pyrometry really is a very common method in soot and lots of diagnostics for combustion. Now, thermal imagers, they can't do ratio pyrometry. They're lucky they can just respond to all the infrared light. So you can't do ratio pyrometry with a thermal imager. But you can with this camera, and you can do it with the native built-in Bayer filter mask. So here's what happens now if you plot the temperature on the x-axis. This is the black body temperature versus the ratio. So it's blue intensity divided by green is the upper curve. The middle curve is green divided by red. And the lowest one is blue divided by red. Now, unfortunately, the blue intensities are really low, and we don't get enough accuracy to use blue. And so right away, that throws out two of these curves. We show them here to be complete, but the blue-green and the red-blue curves are not helpful. However, the red-green, and red is always the brightest for all glowing embers, and the green has the most pixels, so that's also a valuable resource. This gives you a good way of performing pyrometry. Now, the green-red has the advantage of correcting for emissivity and transmittance, but it has a disadvantage that it varies only by an order of magnitude. Before, where we had a turn-down ratio of 4 orders of magnitude, now, if you do ratio pyrometry, you have only 1 order of magnitude variation. And that means that the precision isn't nearly as good. It's a more noisy signal. But if you can buy into the fact that the emissivity times the transmittance is the same for the red as it is for the green, and that's an assumption we make that may have some problems, but it's certainly better than assuming that it equals unity, then you have a method of measuring your temperatures. Okay, so the third bullet here is that the GR ratio, green divided by red, varies only by a factor of 10, and its signal-to-noise ratio is much lower. It's only 6% of the grayscale pyrometry. So the ratio pyrometry, while it's accurate, we believe it accounts for the emissivity and the ash transmittance, but it's not very precise. It's a noisy measurement. And actually, what I'll show in a few minutes is that we think we found a way where we can have the best of both worlds. We can combine the ratio pyrometry for its accuracy and the grayscale pyrometry for its precision. So that's part one. The rest of this talk is going to be 3 parts of this research. So part one is where we take a single ember, we ignite it like this. This is soon after igniting it, just with the butane like a barbecue lighter. It's suspended now on either a piece of wire or a piece, in this case, of silicon carbide. We let the flames blow out, turn on the fan, and get it smoldering red and take some images. And this was published by our group in 2019 in Fire Safety Journal. So it's a whole paper, an entire paper on the method with just one ember. And we analyzed the heck out of this ember and learned how we could speed things up in the future. So this is, I guess, a second, there are 2 or 3 embers in this paper, but only one ember where we show the full temperatures. We're looking at the embers with the lights off, where it says lamp off here, and we could see red regions glowing red and black regions. And it wasn't clear to us what was happening here. There can be a lot going on. It may be that the red regions are burning and they're hot, and it may be that the black is ash, or the black is charred. Maybe it's not burning. Maybe there's burning underneath it. And so what we did is we did some experiments with the lamp on and the lamp off to try to understand that. And this image sequence, I think, helps understand that those black regions, at least for this pair of images, is probably ash. When the lamp's on, those black regions look white. And so as this burns, it leaves ash on the surface. Now, below the ash, you can still have burning, and there's still temperature there that you want to measure, but you need to account for the fact that that ash is absorbing a lot of the photons coming from the under-burning area. Okay, again, these are maple embers. They're small, about the size of diameter of a pencil, 6 millimeters in diameter, and 20 millimeters long. And here, we didn't have a million pixels to work with, but because of the aspect ratio, about 500,000 pixels. So in 1 millisecond, 1.6 milliseconds, take a picture of this ember, and you get 500,000 temperatures. It's really an impressive amount of data that you get with a $1,000 camera. Here's what happened when we took a picture with a thermocouple on the ember. And the arrow here shows where the thermocouple bead is located. And the thermocouple wire was wrapped all the way around the ember, pulled tight to make sure we could get the best thermal contact possible. And yet, the region near the thermocouple bead isn't glowing. the bead in the wire was cool enough that it stopped the burning. But still, we had to try it. It was important to try. And we took this image with the thermocouple. And then this is the image that we're going to analyze next with ratio pyrometry. This was 50 seconds after ignition, a 1 millisecond exposure with F number of 2.8. That's with the lens pretty much open all the way to try to get a fast exposure and to freeze any motion that might happen. It's a turbulent flow field, and so as you watch the red, it does move around. You really want to freeze that motion. And these are the results. So for that particular ember that glows like this in the raw image, if we do at each pixel, get through the ratio pyrometry and go back to the calibration done with the black body, these are the temperatures. So these are the range of temperatures for that ember from ratio pyrometry. We do believe that since it's calibrated with the black body and across the same temperature range of the black body, that we have accounted for the emissivity and the transmittance of the ash. And we get almost a 500,000 pixels of temperatures here. The temperature range is shown there on the scale, 650 to 1150 kelvins. And we had to do a lot of smoothing. The images look grainy. As accurate as this camera is, you still get a lot of graininess, and we smooth them over 7 by 7 pixels. So these are what we believe are the true temperatures of the ember. But we wanted to see if we could improve the precision. In other words, get rid of some of that graininess by looking also at the grayscale method. And so on the next slide, what I'm going to show is the grayscale pyrometry. Remember, in ratio pyrometry, this is the red intensity divided by the green intensity at every pixel, and converting that to temperature with the black body calibration. And in the next slide, what I'll show is just the red intensities calibrated by the black body. And look how much better the precision looks here. Now, because you have that 4 orders of magnitude variation, it's very precise. At every pixel, it's very precise, very smooth. That's the kind of measurement you want. Excellent temporal resolution, spatial resolution, and precision. Your intensities go from 0 up to 2 raised to the 14th power, and each one maps to a different temperature. So if I rock back and forth between the ratio pyrometry, all grainy, and the grayscale pyrometry, nice and smooth, it makes you wonder, is there a way to get the best of both? So the grayscale pyrometry, all these temperatures are lower than we know them to be. Why are they lower? Because there's a little bit of ash, reducing the number of photons, reducing the evident temperature. And the true emissivity is never 1. That's the maximum possible, so probably 0.9. But we believe that we can combine these two to back out this kind of precision without the bias. The way we do that is with the math that's shown here. The first equation is one we've all seen in our heat transfer class, and chapter on radiation. This is the spectral emissive power of a black body. It's a beautiful equation. For those of you who saw Angela Violi this week talking about the ultraviolet catastrophe, this equation accounts for that. It shows the intensity versus wavelength for any temperature of a black body. But we also know that on an ember, while the black body furnace acts like a black body, it's sold as certified to be an emissivity of 0.99 or higher, acts like a black body. The ember doesn't. The ember has an emissivity times a transmittance, mostly ash, maybe a little bit of smoke, that actually reduces the emissive power. And that's shown in equation 2. So what we do here in order to improve our pyrometry is to evaluate equation 1 at the grayscale temperature, at that pixel, whatever the grayscale temperature is, we evaluate equation 1. And we evaluate equation 2 at the ratio temperature. Now, to get to the last equation, sort of the equation 3, we have to pick some wavelength. And so we pick a wavelength of 680 nanometers. It's the first time in this analysis that we've actually picked a wavelength, and it's a little bit of a weakness, but the results don't change that much if you pick a different wavelength in the range of the visible. Then you can back out the emissivity times the transmittance. So we can take those images, the ratio pyrometry image and the grayscale pyrometry image, and then actually, in that 1 millisecond, measure the emissivity at every pixel in our image from this equation. And it's all done in MATLAB or all done in Python. And then we get the emissivity times the transmittance. Now, we do another trick. Okay, so it's kind of a multi-part process. In this step, what we do is something that we've named hybrid pyrometry, where we combine the ratio pyrometry, which is noisy, but it's the true temperatures, with the grayscale pyrometry, which has a downward bias, but very good precision. We do that by taking all the pixels in the image, plotting the grayscale temperature versus the ratio temperature, and they're fit pretty well with just a straight line. And we're lucky that it worked out to be a straight line. There's not too much scatter here. And so then we can introduce this new temperature, which we call the hybrid temperature. It's really a hybrid of the gray and the ratio temperatures by using those A and B fitting constants. And so now, at every pixel, we can get the hybrid temperature. And this is a temperature that has the advantages of the grayscale pyrometry with its excellent precision, and the ratio pyrometry, which doesn't have a bias, which accounts for the emissivity. And so this I'll show then on the next slide, the last slide in this sequence, which looks exactly like the grayscale pyrometry image, except now on the right, and obviously it's hard to see from where you're sitting, the scale is different. So in the legend now, the legend that we show for the temperatures is the temperatures that we believe to be true, the ratio temperatures, but with the nice precision of the grayscale temperatures. And we show also the emissivity here, which goes from 0.5 to 1. And so you can see the emissivity is represented with the same temperatures. This image has a spatial resolution of 17 microns. Again, it's an image taken in 1 millisecond and signal-to-noise ratio of 530. And we estimate the temperature uncertainty at each pixel of about plus or minus 20 degrees C. For that image, we generate a PDF, probability distribution function of all the temperatures. So this is the temperature on the x-axis and the probability of that temperature on the y-axis. And it looks like this. It's almost a Gaussian bell curve. It has a mean temperature for that ember of 930 degrees C, standard deviation of 50. The lowest temperature, the highest, is about 750 to 1070 degrees C. As I mentioned, fortuitously, that's the same temperatures as our black body furnace. And the thermocouple indicated a temperature 230 degrees below this temperature. So anybody in the past who's used thermocouples to measure ember temperatures probably ought to add about 200 degrees to whatever is measured. So let me switch now to part 2. So that was part 1. One journal paper, one image, one ember burning. And some of the reviewers were rightfully concerned that, it seemed like maybe these guys out of Maryland, they take one image and they write a journal paper out of that. When does this end? But we got through the reviews, and I think it's acceptable for what the advances that we made to be able to do it with one ember. We wanted to make sure in our next paper we had hundreds of images. And so what I'll show next is paper 2, where we did actually have a much larger number of images. And this is the paper where we actually spun the camera, as I mentioned, and generated streaks across the camera to see if those streaks had the same temperature as what you would get if the camera weren't spinning. So this is a schematic. It's the same camera, but it's now on a motor and a shaft that can rotate. Rotates at about 1 hertz. And the ember is the same ember as before on a support wire, glowing but stationary. And again, the image that you get from this is exactly the same image if that ember were flying by at the same temperature and the camera were stationary. They're the same embers as before, 6 millimeter diameter, 25 millimeters long. The wind speed was 1 to 2 meters per second, not in a wind tunnel here, but just provided by a case fan, ignited with the butane flame as before. And for this, I want to start these videos. So it doesn't look like much, but I was very impressed that the student with counterweights was able to make Jimmy Baldwin, make these cameras rotate, as I said, at about 1 hertz, and be able to sequence it with an Arduino so it triggered the shutter just as the firebrand came into view. So these are the streaking embers and the emulated firebrands. This is the test summary, so it was a large number of tests. It was a 1,600 images of 15 stationary, 40 streaking embers. So it's kind of a busy test summary there that shows our velocities 1 and 2 meters per second for the wind, and up to 12 meters per second for the streaking velocity. We spun the camera on the horizontal axis and the vertical axis to make sure that there was no impact of the axis. And in the end here, the last 2 columns, the mean temperature is not that different from the stationary ember, and the standard deviation is also similar. Now, in order, as I mentioned, when you're burning wood, you have to get good statistics, you have to do lots of measurements. You can't take a picture of one ember and say, all embers burn at 960 degrees. Well, one ember burned at 960 degrees. But once you have this many, once you have 1,600 images, you can start to get average temperatures and get better statistics. But this is what's required in a lot of fire studies. When you're burning solids, it's not like turning on methane and you know it's 1 milligram per second. That flame is the same the next day when you come back. Burning wood, burning carpet, fire studies require a lot of repeats to get good statistics. And even in a situation where we have very controlled wood supply and exactly the same, we try to ignite it the same every time, there's always a little bit of variation. So this is some of those hundreds of images for stationary embers, and it looks like a scatter plot, it looks like a shotgun plot scattered all over the place, but do notice that the y-axis here, which is the temperature, the mean temperature of the embers, is pretty zoomed in, 820 to 980 degrees C, so we do have enough now measurements to get reasonable statistics on the mean temperature. This is at 1 meter per second, mean temperature versus time. Okay, and we also looked at different distances. It won't really help you if you want to measure ember temperatures, and if you go farther away, you get a different temperature. So we did distances of 0.5 meter, 1 meter, and all the way up to 3 meters, and see that the temperatures don't change with the distance. So that was reassuring. So for stationary embers, we get good statistics, repeatable results, and for different distances, we also get repeatable temperatures. And so next we're ready to start spinning these embers. And these are 6 highly zoomed in heat maps. So these are actually temperatures, now just ratio temperature. And in this case, we haven't been able to make use of the grayscale temperature because for that you would need to know the dwell time. How long was that pixel illuminated by that ember? So for this paper, we've only been doing the ratio temperatures. And whether the camera spins on the horizontal axis or the vertical axis, lo and behold, you get the same temperature. At different distances while it's spinning, you get the same temperature. And so we view this as a successful demonstration of the method. And really now the next step will be able to use it in the field, go to one of those ember showers like I started with, and measure the temperatures with the camera of embers that are flying by. The last bullet here is kind of interesting that we find that the accuracy is similar for a streaking ember as for a stationary ember. And we weren't expecting that at all. But what happens is with the streaking ember, you actually illuminate more pixels. So as the ember is streaking by, you have more pixels to work with to get reasonable statistics. With a stationary ember, it's kind of nice because you can set the exposure and have a brighter exposure, brighter images. But it turns out the accuracy of both methods is similar. Streaking image doesn't necessarily have lower accuracy than a stationary ember. Okay, and then this next will be part 3. In part 3, what we want to do is kind of what I mentioned before, be able to take a picture of a Christmas tree that's burning with this same camera or a similar camera. By the way, we've already calibrated 2 of them, and they had the exact same calibration. So anybody who chooses to buy one of these can use our calibration without a black body furnace. But we'd like to be able to take a picture of a wall burning or a Christmas tree burning, and then measure all the temperatures, all the emissivities, and with shape factors then, suppose this wall were burning, and you take a picture of it, use the shape factor, we can predict the heat flux over this wall and predict whether that wall will start to burn. And so what we're doing now in part 3, and this hasn't been published yet, this is in preparation with Elijah Igwe and Stanislav Stolirov, is to try to measure the heat flux with this camera. Current way of measuring heat flux is with the heat flux gauge. These are beautiful devices, but they're $6,000 typically. You need water cooling, and they only measure heat flux at a point. So if you want to know the heat flux from one wall burning at the other wall, you install one of these heat flux gauges, you run your cooling water, and you get a good measurement of heat flux. But it's a point-wise measurement. Whereas with the camera, if we can map out all the temperatures, all the emissivities, then we have really fine resolution on the source of our heat flux. So in this case, we did the measurements in a wind tunnel. Instead of doing it with the case fan, we actually used a wind tunnel. Here the flow is from the left to the right, and you can see the screen of our infrared camera in front, and you can see just above that the glowing embers. So it's an ember pile. We cook these same kind of dowels over a big propane flame and then pour them into the wind tunnel, seal up the wind tunnel with the window, and start taking pictures of the overhead view. And the overhead view there is with the Sony camera that's going to do the pyrometry. In this wind tunnel, we're limited in speeds, but we can have wind speeds from 1 to about 3 meters per second. And what we want to do is measure the heat flux from this ember pile with the color camera. So here's a test. Here is a test schematic. At the bottom is KO wool. It's kind of like drywall you might have in your house. It's inert. It won't burn. We use it a lot for our fire studies. And we cook these embers and pour them onto the KO wool in a rectangle that's shown there. That's the firebrand pile dimensions, 12 by 3 centimeters by about a ½ centimeter high. Then the tunnel is blowing. The wind is blowing. We cover the top with this glass and start taking pictures with the camera. And just next to the camera is our heat flux gauge. So this is a Medtherm heat flux gauge, and it's just a point measurement. It's a very wide angle, 150-degree angle. It picks up all the heat flux in that range. But it measures, with about a 1-second response time, the heat flux at that spot. So the idea with this measurement is that we're going to use the camera to measure the temperature at every pixel and the emissivity of every pixel. And then with shape factors, find out what is the heat flux at the heat flux gauge. And this is something that's never been done before. These heat flux gauges, as I mentioned, they're expensive. They only measure radiation at a point. If we can use a color camera to get a fully resolved measure of that radiation, it's less expensive and it's a lot more useful information. Okay, so in order to map this, what we do is we get a picture of the ember pile, get all the temperatures and emissivities, and then apply these shape factors. So I think all of us have had this in elementary heat transfer, is a shape factor analysis, and that's given by this equation here. So the intensity of radiation that goes from the bottom rectangle to the upper rectangle is given by this equation. It depends on pi times the distance squared and the angles cosine theta I, theta j. But in Python, this is a relatively simple calculation to do. So if the camera knows for every pixel its temperature and its emissivity and its relationship to the heat flux gauge, then you can sum over all the pixels and estimate the heat flux at the heat flux gauge. So first, let me show you the temperatures of the ember piles. These are shown here. On the left is the raw image. It looks mostly black, and that's because when you take these images, if you turn up the exposure bright enough so that you can see it well with your eyes, then all the red pixels will be saturated. And so you can't really do ratio pyrometry or any other kind of pyrometry if you're maxing out your red signal. All you know is that it's too bright for the camera. So in order to avoid that, you want a few pixels saturated. You want to use the full range of your camera, but not too many. You know, out of a megapixel, out of 1,000,000 pixels, you can probably tolerate 10 pixels that are saturated, or maybe 100. So image on the left is the raw image. It looks very dark, but that's by intention. And then when you convert this to temperatures from the ratio pyrometry, you get the temperatures that are shown on the right. And you can see from the wind coming from the left to the right that it blew some of those dowels. They're round and they tend to roll. It blew them out of the original rectangular space downstream. And you can also see the temperatures. So again, they're going from 600 to 1100 degrees C. So these are all the temperatures. We don't show the emissivities, but we have them as well. Or actually, as an alternative, you can just assume a constant emissivity. Here we're using, if you assume a constant emissivity of 0.8, that seems to do a pretty good job. And then we'll map all these temperatures with the shape factors back to estimate the heat flux at the heat flux gauge. First, these are what the PDFs, the probability distribution functions, look like for these embers at the different velocities. Usually what we see for smoldering is that the faster the wind is blowing, the higher is the temperature. And it doesn't seem to have any limit. We've done this with even choke flow orifices, you know, high pressure air jets blowing on these dowels. And the dowels get brighter and brighter and hotter until the force of the air is so strong that it breaks apart and flies and the experiment's over. So it's not like a candle. Candle, when you blow on it, it goes out. With an ember, when you blow on it, it seems to get hotter. It's my hypothesis that it will always get hotter. But nobody's ever really demonstrated this. Seems to me intuitively, eventually, if you blow it fast enough, the kinetics won't keep up with the temperature, and it should start to cool or maybe go out. But at least for this range, 1, 2, 3 meters per second, you can see in these temperatures that the higher the wind speed, the higher is the temperature, average temperature of the pile, or the temperature distribution. And again, we're lucky that all these temperatures are pretty close to the range of temperatures where we calibrated. We don't have to do much extrapolation beyond the limit of our black body. And then, really, what this is all leading up to is the last plot, last set of 4 plots, which is the heat flux. So here what we're doing is we're taking the camera, taking a picture of the embers, getting all the temperatures, mapping them up with the shape factors back to where the heat flux gauge is, and then comparing these two outputs. So for 4 different wind speeds, as I mentioned, the higher the wind speed, the higher the temperature. We're plotting the heat flux versus time. So we use the camera not only to measure temperature, but to measure emissivity, and now also to measure heat flux at any point in the view of the flame. At the lowest temperatures in the upper left, you can see there's a big difference, almost a factor of 2 difference because the signal is so low. But as you go to higher and higher wind speeds, and especially to the image on the lower right, 2.7 meters per second, the heat flux that's measured by the heat flux gauge is in very good agreement with the heat flux that's predicted by just using the camera with ratio pyrometry. And with that, I think it's time for a break.